Today we're unpacking this explainer on Crankcase Acoustic Tuning. Now, as engineers, builders, or just serious gearheads, you already know an engine is essentially a giant air pump. But what happens to the air trapped underneath those rapidly moving pistons? Well, today we're going to treat the bottom end of the block not just as a dumb oil reservoir, but as a complex, highly tunable acoustic environment. It's a total game changer. Here's our game plan for today. We'll start with the third acoustic timbre, look at the physics of crankcase resonance, cover the symptoms of acoustic failure, dive into tuning street and race engines, and finally, wrap up with diagnosing pressure and leaks. Okay, section 1, the third acoustic chamber, understanding the hidden environment. Now, while a lot of people obsess over intake and exhaust plenums, they are completely ignoring the literal acoustic storm happening right below the pistons. The air down there isn't static, right? It's violently compressed, expanded, and agitated thousands of times a minute. So the crucial takeaway here is that the crankcase is a highly tunable acoustic environment that directly dictates engine health. Crankcase Acoustic Tuning, or CAT, is the engineering discipline that brings order to that absolute chaos. By deliberately shaping the ventilation system and internal volumes, we manage those pressure pulsations. And when we control this space, we minimize pumping losses, prevent oil aeration, and keep our dynamic seals intact. Think about the mechanics for a second. Every upstroke creates a vacuum, and every downstroke compresses air. It acts exactly like sound waves bouncing around inside a closed pipe organ. Add in the high-velocity, incredibly hot blow-by gases escaping past the piston rings, and you've got a broad-spectrum noise source exciting resonances across the entire crankcase. If we don't deliberately tune the internal geometry, the ribbing, the windage trays, the baffle shapes, these overlapping pulses will create incredibly destructive standing waves. Moving right along to Section 2, Physics of Crankcase Resonance. Let's look at the math behind the madness. Because these pressure oscillations, they're entirely predictable. They're tied directly to engine RPM, the number of cylinders, and the stroke. Let's put a number on this. At 6,000 RPM in a four-cylinder engine, overlapping piston pulses create a continuous 200 Hz pressure wave. Here's how the math shakes out. You take your RPM, divide by 60, and multiply by half the number of cylinders. So 6,000 over 60 is 100. Multiply by 2, boom, 200 Hz. That is a massive, continuous acoustic wave just propagating through the block, reflecting off walls, and building amplitude if we don't manage it. So how do we stop those 200 Hz pulses from literally tearing our seals apart? We use Helmholtz resonators. We carefully match the resonator volume to the crankcase volume to cancel out those dominant frequencies. If you need a refresher, a Helmholtz resonator is simply a cavity with a specifically calculated neck dimension. When that 200 Hz pressure wave enters the cavity, the resonator creates an opposing wave that destructively interferes with it. Actually, scratch that, it doesn't just interfere. We are literally canceling out the specific destructive sound waves before they can even build up. Now, you might be wondering, what about the walls of the engine itself? It's not just about chamber volume. A highly polished surface acts as a perfect acoustic reflector, bouncing that wave right back with zero energy loss. But we use rougher cast surfaces, usually around 3.2 to 12.5 micrometers, to actively absorb that acoustic energy. Sometimes, in dedicated racing engines, we'll even apply specific textured coatings or thermal barriers to the crankcase floor just to strategically shift those resonant frequencies lower. All right, Section 3. Symptoms of acoustic failure. What happens when unmanaged pressure strikes? Basically, what exactly breaks when our math is wrong? Listen to this. Unmanaged crankcase pressure can cost us up to 8% of peak power, just from parasitic windage friction. High pressure creates this dense, aerosolized air-oil atmosphere. When your crankshaft and connecting rods have to constantly churn through that thick, heavy mist, it acts like aerodynamic drag. It robs you of power and drives up oil temperatures. But with proper acoustic tuning and windage control, we can drop that parasitic loss all the way down to 0.5%. That's huge. And the mechanical damage? It gets way worse from there. High-amplitude pressure oscillations directly lead to oil aeration. This aerated oil destroys bearings and forcefully pushes past dynamic seals. If you're seeing blue smoke on startup with absolutely no external leaks, or rear main seals weeping repeatedly, or even sudden ring flutter at high RPMs, you're likely looking at an acoustic resonance issue. The pressure waves are literally atomizing the oil and suspending it, pulling it right through your PCV system, or actively fighting the oil return to the sump, which starves the main bearings. It's a worst-case scenario.
Moving to Section 4, Tuning Street and Race Engines. Let's look at the actual application and design.
How do we engineer these solutions differently for a daily driver versus a dry sump track car? Well, notice how proper catch can sizing maintains necessary acoustic impedance, which is just the resistance to airflow. A street engine relies on a carefully tuned closed-loop PCV system, pulling a mild vacuum to help seat the piston rings. But a racing engine, it uses active dry sump scavenging to pull a deep vacuum down to negative 30 kilopascals. If you completely remove the air, sound waves literally can't propagate. It is the ultimate acoustic fix. Also, take a look at the baffle passage sizes. They have to be large enough for oil to return, but small enough to act as acoustic resistors that divide the lower block into smaller, non-resonant subvolumes.
Now, for you guys working on turbocharged, high-output projects, proper catch can volume and check valves are absolutely vital to manage those massive blow-by rates. When a turbo spools up, it pressurizes the intake manifold, which instantly eliminates the vacuum signal that normally drives the PCV system. If you don't route a dual-path system with one-way check valves, that boost pressure is going to backfeed right into the crankcase. The result? An instant, catastrophic pressure spike that will absolutely blow out your seals. No question. This is why we constantly see aftermarket modifications totally ruin our work. Enthusiasts love to bolt on these flashy aftermarket valve covers that are completely hollow inside. What they don't realize is that the ugly factory labyrinths they just threw in the trash were specifically acting as Helmholtz resonators and acoustic dampers. Removing factory ventilation baffles destroys those dampers and guarantees an erratic idle. Without them, you get howling noises, massive oil carryover, and incredibly unstable crankcase pressure.
All right, final section, Section 5, Diagnosing Pressure and Leaks. Let's open up the technician's toolkit.
Let's see how we map and resolve this resonance in the real world. Start simple, use a digital manometer at the dipstick tube. A healthy street engine should show a slight vacuum at idle. If it passes that, check your PCV flow rate. Honestly, if the blow-by is too high, no amount of acoustic tuning is going to save you. For advanced diagnostics, we mount a high-speed piezoelectric transducer, run the engine on a dyno, and log the pressure amplitude as the RPMs climb. What we're looking for are distinct spikes that tell us exactly where the engine is resonating.
And this is where fast Fourier transform, or FFT analysis, becomes absolutely vital. It proves whether that weird noise you're hearing is an RPM-dependent piston pulse or just a failing bearing. By running an FFT on the transducer data, we break down those complex pressure waves into their specific frequencies. If the dominant frequency matches our primary piston pulse math, like that 200 Hz we calculated earlier, boom, we know for sure we have an acoustic resonance problem. If it doesn't match, then we start hunting for mechanical wear in the valve train or accessories.
Keep this diagnostic checklist handy. It's great for identifying common air leaks in ventilation hoses or just verifying if your internal block baffles are functioning right. Pro tip, never ever assume a PCV whistling noise is normal. Whistling or hissing means there is an unmanaged velocity spike, which is usually caused by an incorrect PCV valve flow rate, an improperly sized aftermarket catch can, or blocked internal baffles. Remember, the length and diameter of your breather hoses directly determine the resonance frequency and the wave amplitude of the whole system. And one word of caution on vacuum. While stable vacuum is absolutely necessary for consistent power and reducing oil aeration, going beyond negative 30 kilopascals risks extreme rear main seal inversion and ring rail collapse. With active dry sump scavenge pumps, it is entirely possible to pull too much vacuum. If you exceed the design parameters of your seals, or if you run a low-tension ring package, that massive pressure differential will literally fold the seals backward, pulling dirt and outside air straight into your crankcase. So, what does this all mean? Ultimately, crankcase tuning transforms a chaotic pressure storm into precise, managed airflow. Ask yourself, are you tuning the whole engine or just the parts you can see? You can have the most beautifully designed intake manifold in the world, but if your internal block geometry is amplifying destructive standing waves, you are leaving power, efficiency, and reliability on the table. The crankcase is a meticulously engineered instrument. Make sure it's playing the right tune.